Hello, welcome back. In this video, I want to talk about transformers and gyrators. And at the end of this video, we are going to navigate through a specific gyrator, which is called a DC motor. If you remember, examples of transformers were gear chains, levers, or electrical transformers. We mentioned that one of the fundamental ideas in these transformers was that they connect the effort on the first side, let's say this is the first side and this is the second side, to the effort on the second side with a constant number. Similarly, we mentioned that they connect the flow on the second side to the flow on the first side by a constant number. For instance, in gearboxes, we had N1 as the number of teeth in gear 1, N2 as the number of teeth in gear 2, or similarly in electric transformers, we had N1 as the number of windings in gear on the first side, okay, and then N2 as the number of windings on the second side. If you assume that the effort here is T1 and the effort here on the side 2 is T2, which effort, if you guys remember, was a force kind of character. And the flow here is theta dot 1 and flow here is theta dot 2. We had a formula for these gearboxes that T1 was equal to the number of teeth in gear 1 over the number of teeth in gear 2, T2. Similarly, we had theta dot 2 equals to N2 over N1, sorry, N1 over N2, theta dot 2, theta dot 1, I'm sorry. Now you see that this is in fact the same formula that we have here. We have the interaction between the efforts and also the interaction between the flows. And if you guys remember, if you write down the equation for electric transformer, okay, then for these electric transformers, you had basically the voltage on the first side and the voltage on the second side, okay, and also the current on the first side and the current on the second side, okay. And you see that you will get very similar formula that E1 was equal to N1 over N2 E2, and then I2 was equal to N1 over N2 I1. Very similar idea, yes? Now, we want to talk about something different. We want to talk about a device, okay, such as DC motor, such as centrifugal pumps, okay, centrifugal pumps, that connects the effort on the first side to the flow on the second side. Similarly, they connect the effort on the second side to the flow on the first side, okay? And this is going to be a number again, okay, that we are going to use here and here. Sometimes these numbers are the same, sometimes they're not, okay? But this is the idea behind these new devices, and we call them as gyrators. So gyrators are different from transformers in a way that, if you remember, transformers were devices that connect the effort on the first side and the effort on the second side, and we have flow on the second side and the flow on the first side. Here we have the effort on the first side and the flow on the second side, okay, and also effort on the second side, flow on the first side, okay. So with that in mind, let's go and talk about DC motors a little bit, okay. DC motors are devices that somehow if you provide electricity to them, normally, they will provide a mechanical rotation for you, okay? And we use DC motors a lot as actuators. Actually, they are very, very valuable for us. When we want to talk about DC motors, we talk about interactions between the magnetic field and electric field. Okay? And all the things that are happening inside the DC motors are basically based on three laws of physics. The first law of physics is how you can change a wire to a magnet. Okay? So, if you have a very simple wire, just like the one that I have here, okay? Just like the one that I have here. This is my wire, yes? The red one. If you have a simple wire and you somehow apply some current in that wire, okay, you are gonna change that wire to a magnet. Basically, you're gonna induce some magnetic field around that wire. These magnetic fields would be circular, okay, and you can assume that your wire is at the center of those circles. If you want to know the direction of that magnetic field, okay, which we show it with B, okay, and the units for this one is Tesla. So you will use the right hand rule. You hold the wire in your hand, in your right hand, and your thumb shows the direction of the current. The way that your fingers close show the direction of magnetic field. Once again, you hold the wire in your right hand and your thumb in the direction of the current. The way that your fingers, the direction that your fingers close shows the direction of your magnetic field. Okay, so this is the first law. How you can change a wire into a magnet. The second law is, okay, look at this. If you apply some current to a wire, you're going to change that wire to a magnet, yes? So I have this question for you guys. What happens if you put two magnets adjacent to each other? Well, have you guys done it before? If you put two magnets adjacent to each other, you would see that they will interact with each other. They might attract each other or they might push each other away. Okay, and that's exactly what's happening if you put a wire that carries a current like this, okay, in a magnetic field. Imagine that I have an established magnetic field, okay, which starts from the North Pole and goes to the South Pole, okay, and this is an external magnetic field, yes? So when I put my wire in this existing magnetic field, which my wire right now has a current passing through it, so it's already a magnet. I put it in another magnet or adjacent to another magnet. That second magnet, which is the external magnetic field, will apply some force to my wire. Okay? So for knowing the direction of and magnitude of that force, you can use this formula. The force is basically L, which is the length of the wire in that magnetic field, multiplied by I, which is the current, cross magnetic field. You guys notice that I and B are vectors. Okay? So again, the length of the wire in the magnetic field, the current that passes through the wire, okay, and the magnetic field vector. So to show the direction of this force, we use the right-hand rule. Again, put your four fingers in the direction of the current, yes, of your right hand. Close your four fingers in the direction of the magnetic field. Your thumb shows the direction of the force. Once again, put your four fingers in the direction of the current, close them in the direction of the magnetic field. Your thumb shows the direction of the force. Okay? So, how? The second rule is basically how a magnetic field and a wire that has or carries a current will interact with each other. They're going to interact, they're going to apply some force on each other. Yes? Now, there would be a happy scenario here when your wire or your current and the magnetic field are perpendicular to each other. If they are perpendicular to each other, then this vector formula, so I forgot to mention that force is also a vector, okay, in this formula. This vector formula will reduce to a scalar. So your force would be just LIB or BLI, okay, doesn't matter. So you just put the magnitude of these guys, okay, and or the magnitude of these vectors, okay, so L, the magnitude of I, the magnitude of B, okay. So just for notational simplicity, I'm going to drop the absolute values because I'm not showing them with vector. It means that I'm referring to their magnitude. Good? Okay. So the second law was how a current or a wire carrying a current interact with a magnetic field. Okay. So the last law is the weirdest of all. Okay. How? If you have an existing magnetic field, let's say that I have this external magnetic field from north to south. Yes. So this is my external magnetic field. Okay. And I have a wire, just a simple wire. Okay. And I start to move that wire in that magnetic field. I'm going to change that wire to a small battery. Yeah. Again, if I have an existing magnetic field, yes, and I have a simple wire, nothing but a simple wire, and I start to move that that wire in the magnetic field, I can possibly, with some conditions, I can change that wire to a small battery. Yeah. How? We say that if you have this wire, okay, then the voltage that your battery, your small battery, will be generating would be the velocity cross the magnetic field dot the direction or the length of the wire. Good. Again, guys, if you are lucky and your magnetic field and the direction of the motion, the velocity, are perpendicular to each other, you can basically get rid of this cross product, and this is going to give you a scalar value. Yes. Again, guys, look at this. Since this is a cross product, you can again use the right hand rule for this one. Put your 4 fingers in the direction of the velocity, close them in the direction of the magnetic field. Your thumb should show the positive polarity of the battery when you project it on the wire. Yes, when you project it on the wire. So for instance, in this example, if you assume the velocity of the wire going upward, okay, and if you assume that your magnetic field is actually going from the north to the south, using the right hand rule, okay, with me, you see that your positive polarity of the battery is basically pointing to the direction that I showed in the picture. Okay, so this is the last law. Okay, how you can change a wire to a battery or a voltage source. Yes? Okay. So, by the way, guys, we call this voltage that is induced in this small wire as back electromotive voltage. Okay, and there is a reason for that. Okay, it's historically it's called back electromotive voltage. There is a reason for that. Okay, and I'm going to explain that reason right now. Okay, imagine that your wire had an existing had an existing current. Yes. Okay, in a way that I showed you in the blue. Okay, and so law one says that, okay, if you have an existing current, then you're going to change that wire into a magnet. Okay, and law two says that, okay, now you have two magnets adjacent to each other, which is the existing magnetic field and the wire in the wire with the current. Okay, now these two guys are going to apply some force with on each other. Yes, so because of that force, imagine that your wire actually goes upward. Yes, so because of the force that we have here, okay, in the second law, if you use the right hand rule, you see that the force is going to be applied upward. Because of that upward motion, you're going to end up with upward velocity. Yes, okay, so with that velocity, now the third law is activated. Okay, when the third law is activated, you're going to change that wire to a small battery. Okay, and if you use the right hand rule with the third law, if you assume that the wire is actually going upward, you see that you have a small battery, which the positive polarity of this battery is going to be like this. Yes, it sounds like it's generating a current that is opposing the existing current in the wire. Okay, and because of this opposition, because of this, we call this as back electromotive voltage. Okay, so it somehow opposes the direction of the already existing current in the wire. Okay, now let's see how we can put these three laws together, okay, to make sense out of them into an electromechanical device, which is a DC motor. Okay. DC motors work with the interaction of magnetic field and the electric field. Okay. What we are looking here is a permanent magnet DC motor, okay, which they come with an existing magnetic field, okay, which we call it as magnetic field of the stator. So stator, these guys, is stationary, okay, and you can assume that stator is a big magnetic field. These stators, they provide the magnetic field in a specific way that somehow they are perpendicular to what we call it as the rotor. Okay, so these magnetic fields that these guys are providing, are all of them are perpendicular to the rotor. Okay, when you see perpendicular, you'll see that, okay, well, if the magnetic field and the direction of the current, or something with direction of velocity, are perpendicular to each other, then all these cross products are somehow, for me, are going to reduce to a scalar product. Okay, so perpendicular for you should be a buzzword right now. Yes, so it means that something good is happening. Okay, so let's look at this rotor, okay, that is inside this stator. Rotor is basically a shaft, okay, that it has some stack, okay, and somehow on this shaft, okay, you have wires or windings on the periphery of this guy. So behind this, you see that there are wires like this, okay, on the periphery. Okay, so if you look at them from the cross-section area, you see that you have one wire here, for instance, and one wire here. Okay, they're going into the plane. Okay, and we call this rotor with the windings and everything, okay, as armature. Okay, and these armatures are supported by some bearings as well. Okay, so you see that these armatures, they have windings, yes, here, 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 and here. Now, imagine that for these armatures, okay, I have a magic that somehow, in a way that I am gonna power up, or I'm gonna send current to the wires on the top part of the armature in a way that the current goes into the plane. Okay, and I'm gonna apply some current on the wires below or on the second half, okay, in a way that the current goes out of the plane. Okay, and the way that we do apply these currents is through something that we call it as brushes. Okay, and these commutator. Okay, we are gonna apply these brushes, okay, on these commutators. Okay, and these brushes are actually going to be sliding on these commutators. Okay, so in a way, okay, and they're gonna power up each of these guys when they are in contact with them. Okay, now look at this. We're gonna use the three laws that we discussed. Yes. Okay, imagine, let me just get rid of all these wires and I'm going to keep only two of them. Okay. So when I apply a current on this specific wire, okay, you see that because of the first law, I'm going to change that wire to a magnet. And since I have an existing magnetic field from the stator, okay, now the second law actually kicks in, okay, and I see that I'm going to have a force that's applied on that wire. Because the magnetic field and the wire are perpendicular to each other, if you use the right hand rule, okay, and the second law, you see that you're going to have a force that is applied on this direction. Yes, on this wire. So I keep my four fingers in the direction of the current, which goes into the plane. I close them in the direction of the magnetic field. My thumb shows the direction of the force. Similarly, if you look at the wire, okay, on the second half of the picture, you see that, for instance, for this guy, since the current is applied out of this plane, okay, I put my four fingers in the direction of the current. I close my four fingers in the direction of the magnetic field. My thumb shows the direction of the force. Okay, so you see that forces on the top and the bottom are gonna twist this rotor. Yes, they're gonna twist this rotor. They're gonna rotate it. Okay, and because of that, you're gonna end up with a mechanical motion, a rotation. Yes. Okay. Now look at this. This was just one wire. Okay. Assume these two wires. Assume these two wires. You see that? All of these wires on the top and all of these wires on the bottom, they're going to have some torque applied on them. Okay, that we're going to talk about that in a bit. And these torques are going to be added to each other. Okay, and at last they're going to give you a mechanical motion. Great. Okay. Now imagine that you have the arm or the radius of this rotor or the armature as R. Okay, then you see that for each of these wires, okay, for each of these wires, your torque would be R cross F, if you remember, yes? And since the radius and the force are perpendicular to each other, I can reduce the cross product to a simple product, yes? So RF, yes? Okay. And this is just for one wire, yes? So it's going to be just one wire. Now, let's go ahead and substitute for F, the force, from the second law, okay? The second law says that the force is going to be what? The force is going to be L, I, B. Since the current and the magnetic field are perpendicular to each other, yes? Okay, now look at this. I can rewrite this. Yes, I can rewrite this with R, L, B multiplied by I. Yes. Why? Because R is constant. It's the radius of the rotor. Yes. L is constant. It's the length of the wire in that magnetic field. And B is constant. Why? Because B is the magnetic field that's provided by the stator. Okay, so this one is also constant. So I have a constant number that's multiplied by I, and this is just for one wire. If I sum them up across all the wires, yes, then I would basically lump the effect of all of these guys, okay, and I would have it as Kmi. Km is a constant number. We call it as motor torque constant. Okay, so you see that the beauty of this formula is that I have Tm, or T of the motor, equals to Kmi. T is a torque. It's a mechanical effort. I is the current. It's an electrical flow. You see that this device was able to connect the effort on the mechanical side, which is E2, to the flow on the electrical side, okay, which is F1. Yeah, okay. Now, there is another important formula for the DC motors as well, okay? Guys, note that the minute that any of these wires start to move, you're going to have back electromotive voltage, yes? Okay, so the minute that you have a motion for these guys, okay, then you have a back electromotive voltage, okay? And that back electromotive voltage is going to be BLV, yes? Okay, now, look at this. This is your rotor, yes? And velocity of each of these wires is basically shown with this guy, yes? With this vector. If you remember from your kinematics courses, how can you basically find the linear velocity from the angular velocity? Theta dot, let's say, okay? If you guys remember, you had this formula, yes? V equals to R theta dot, yes? If R and V are perpendicular to each other, okay? Then if you substitute V here, okay? So let me just bring this one a little bit to the right. If you substitute V here, then you will have B, L, R, theta dot. Yes, this is just for one wire. You need to add them up on all the wires, okay? And if you add them up, you see that B, L, and R are constants, and you can lump them in one constant. We call it as KB, okay? And this is going to be KB theta dot. And you see that in formula and paper, okay, KB and KM are the same. Yes, KB and the same, KB and sorry, KB and KM are basically the same formulas. Yes, okay. We call KB as back electromotive constant. Okay, so let me summarize the formulas in DC motors. You have Tm, or T of the DC motor, equals to Kmi, and you have back electromotive voltage of that DC motor, which is working against you, okay, as KB theta dot, okay? And the important observation here is that they're not like transformers. They're actually different because they somehow connect the effort on one side to the flow on the second side, okay? So in these formulas, you have E1 equals to, or E2 equals to Km F1, okay? And you have E1 equals to KB F2, okay? So with this introduction, okay, let's go and see how we can actually model these devices. Okay. What we can do is with DC motors, we can actually somehow consider two energy domains for these guys. The first energy domain is the electrical side, okay? And the second energy domain is the mechanical rotation. The electrical domain is the one that deals with the wirings and back electromotive voltage and all the resistance and inductance because of the windings. Yes. Okay. So we basically lump all the resistances in one RA, or the resistance of the armature. We lump the inductance of the windings on the periphery of the rotor in one inductor element. We consider back electromotive voltage, okay, as basically a small battery here, okay, and this is going to be the voltage that we support. This is the DC voltage that we support to that DC motor. Now, this DC motor, when you apply some voltage on it, okay, it's going to give you a torque. Yes. And we kind of consider that torque as an input to the mechanical side. All the bearings that are supporting the rotor and the armature, we lump them in a viscous friction model. Okay. And also, we consider the moment of inertia of the rotor as a J. At the end, we can consider a little bit of torque load on this rotor. Okay. So this is something that we have to overcome. Okay. So you see that clearly I have two domains of energy. I have electrical and I have mechanical. So what I would do is I would basically divide my page into two parts, okay? And I'll call the first one as electrical. And the second one would be the mechanical rotation. Okay? So what I would do is I would basically follow my four-step approach for each of these domains separately. And at the very end, I'm going to use the equation for the gyrator, okay, to connect one energy domain to the other side. Okay, what was the equation for the gyrator? If you guys remember, we had torque of the motor equals to Km multiplied by I, okay, and which I'm going to show it with I of armature. Okay, and also we had back electromotive voltage equals to KB theta dot. Yes? Okay. So let's get into it. Okay. So what we have here is basically an electrical domain and a mechanical domain. So what I'm going to do is first I'm going to go to my step one. Okay. And I'm going to list the elements on the electrical side. Okay. Now we have done this one before. Okay. This is very simple. I'm going to have it as inertia, stiffness, friction, okay, and my sources, and the number of ODs. Okay, so look at this. For inertia in electrical systems, if you guys remember, it was the inductance, yes? So this is going to be LA. For stiffness, we had the capacitors. Unfortunately, we do not have any capacitors in this problem. For friction, we're going to include the resistance. So R of the armature is our resistance element. The sources for this problem, if you look at this, you see that I have E input and back electromotive voltage. And if you guys see, they are working against each other, yes? So I'm going to have it as En and back electromotive voltage. And at last, I need to comment on the number of ODs. How many ODs do you guys think I would need for this system? Okay? If you remember, the number of energy storing elements will mandate the number of ODs. Since I have only one inductor, Okay, so I would end up with only one ODE. Okay. Now let's go to step 2 and find the dynamic variable. For this problem, the dynamic variable is the current that passes through the inductor. Since I do not have any capacitor, I would call it as I sub A. Now I would go to next step, which is writing down the ODE for that energy storing element. Yes, so write down ODE for the energy storing element. Okay, look at this. I had the inductor, so I'm going to write it down as ELA equals to LA I dot A. Okay, now if you guys remember, we are going to go after the good terms and not good terms. Our good terms were dynamic variables and the inputs. Our not good terms are everything else. So I dot A is a good term since it is my dynamic variable. Well, it's actually the time derivative of the dynamic variable. And ELA, you guys tell me, is it good, not good? Well, you know that. It's not a good term since it's not my dynamic variable. And notice that LA is a parameter, it's constant, we don't care about that. Okay, so I would go to step 4, okay, and my whole job in step 4 is rewriting the not good term in terms of my good terms using KVL, KCL, and Ohm's law. Yes, so rewrite the not good term using KVL, KCL, and Ohm's law. Okay, so look at this. What are my options? Can I write down KCL for this problem? Well, I need a node. I do not have a node in the circuit. But however, I can write down a KVL. Okay, so let's go ahead and walk on this circuit in the direction that I showed. Convention 1 says that because I'm moving in the same direction of the current, the voltage across the resistor and the inductor drops. Then I hit the positive polarity of this battery. Since I hit the positive polarity, the voltage dropped here too. And when I get to the En, I hit the negative polarity of the battery, the voltage rises. Okay, so my KVL would be negative ERA, negative ELA, negative EB plus En equal to 0. Yes, okay. With that in mind, I would go and write down the Ohm's law as well, okay? And you guys know that from the Ohm's law, ERA is equal to RA IA. Okay. Now, if you substitute Ohm's law in the KVL, okay, so substitute Ohm's law. In the KVL, you will have negative RAIA, negative ELA, negative EB plus En equal to 0. Yes? Okay. Now, if you solve this equation for ELA, okay, then you will have E input minus EB minus RA. IA. Okay, let's call this equation as equation 1, okay, and let's go back and call this equation as equation smiley. Okay, substituting equation 1 in a smiley, what do you get? So substitute 1 in a smiley, you will get, let me just rewrite equation smiley here. ELA equals to LA I dot A. Okay, and if you substitute equation smiley, equation 1 for this guy, okay, you will have basically, instead of ELA, okay, you'll have EN minus EB minus RA IA. I forgot to mention, guys, in equation 1, everything is a good term. IA is a good term. It's your dynamic variable. EB is an input somehow, and EN is an input. They're all good terms, yes? So that's why actually we substituted equation 1 in equation smiley. Okay. Now, before moving forward, okay, you guys notice that there is a link in this equation to the mechanical side, and that link is coming from EB. Where did we have EB? We had it here. Okay, so in fact, this is a gate to the mechanical side. Okay, so let's go ahead and substitute for EB. Yes, so I'm gonna substitute here as let me just keep this one here. Okay, and substituting EB as KB theta dot. Okay, then you will have EN minus KB theta dot minus RA IA equals to LA I dot A. Okay, now keep the input on one side and bring all the dynamic terms to the other side. Check for the signs. If the signs match, you can box these equations. Okay, so you can have EN equals to LA I dot A plus RA IA plus KB theta dot. Okay, and you see that in this equation I have two families, family of IA, family of theta dot. For family of IA, I have two members. There are no sign mismatches within IA and I dot A, the two members. And family of theta dot, I have only one term. This family is linked to the other side, to the mechanical side. Yes, so I still need to go and check that side out. Good? Okay. Now, so let's go to the mechanical side now. Mechanical side, the elements that we have are inertia again, stiffness, friction, our sources, and the number of ODs. Okay, so let's comment on these guys, okay, and then go to the step 1 and solve this part. Okay, so what I'm going to do is I'm going to go after the inertia first. Inertia is the inertia of the motor, okay, the rotor. We have it as J here. I'm going to put it J. Stiffness in mechanical systems are springs. I'm not considering any stiffness in this problem. Friction comes from the bearings. I assume that there is a viscous friction here. And the sources here are Tn, which is basically the torque of the motor, okay, and also TL. This is a load torque from the environment. This is something that I need to overcome, okay? However, look at the Tm. Tm is actually your link to the electrical side, okay? And we're gonna substitute for Tm at the end. Now, here's a question. How many of these guys do you guys think that I would need to model for this system, to model this system? Well, I have only one independent motion, and that's the motion of the rotor. So I would end up with only one OD. Okay. Now let's go to a step 1. And select your coordinate system. Okay. For this problem, I assume that the coordinate system, if I step aside and look at the system, I assume that the coordinate system is actually going clockwise direction. So I'm going to consider it as theta going clockwise direction. Step 2 is basically the isolate your inertia elements. What do I mean? Grab it, disconnect it, and throw it on a piece of paper. So this is going to be plus theta going clockwise direction. So this is plus theta going clockwise direction. Okay. And I'm just going to isolate that one. Yes. Okay. So in step 3, what I would do is I would go on sketch the free body diagram. Okay. In the free body diagram, I would go after few CSR. Okay. Friction, external weight, contact, spring rope. We have done this one so many times right now. Yes. So first of all, friction. My friction torque is coming from the bearing. The magnitude of this one is known, b theta dot. The direction, I would look at the direction of motion. If I assume that I'm going to go positive, basically positive direction, this is going to go negative. The next one are the externals. I have two externals. One is Tm. Look at the setup. One is Tm, is in the positive theta direction, and the other one is T load. It's working against the direction of motion. Yes. So Tm and T load. Tm positive theta direction and T load is negative. Next one is the weight. Weight is applied at the center of rotation. No arm to generate any torque for me. Yes. Contacts are actually passing through the center of rotation. I have no spring. I have no rope. I'm done with the free body diagram. The next one is step 4, which is basically the equation of motion. So let's formulate the Newton's second law. Summation of torques along theta equals to J theta double dot. Okay. And for this problem, you see that I have 1, 2, and 3 torques. Tm is positive theta direction. TL and B theta dot, negative theta direction. Yes. So let's go ahead and put them here. Tm, negative TL, negative B theta dot equals to J theta double dot. Okay. Before moving to the next part, guys, note that your Tm is your connection to the mechanical side. Yes. So this is going to be Km I. Where did I get this equation? From here. This is the equation for your gyrator. Yes. So this is going to be Kmi of the armature. Okay. So now keep the input on one side, bring all the dynamic terms to the other side, check for the signs. If your signs match, you can box these equations. Yes. Okay. So sorry, I'm gonna keep TL on one side. So negative TL equals to J theta double dot plus B theta dot minus Km IA. Okay. And you see that I have two families here. Family of theta, which has two members, theta dot and theta double dot. And family of IA, which has only one member. There are no sign mismatches among the members of each family. Okay, I can box this equation. Okay. Now, let's look at this. I have, let's call this equation as equation 2 and equation 3. Yes? Okay. These two equations are the equations that governs the dynamics of my DC motor. You see that equation 2 is a first order differential equation. Equation 3 is a second order differential equation. Okay, so the total order of the system is 1 plus 2, it's going to be 3. However, in equation 3, there is another option. If you assume that your theta dot is omega, then theta double dot would be omega dot. Okay, with these assumptions, okay, then you can rewrite equation 3 as negative TL equals to J omega dot plus B omega minus KMI. Okay, and also similarly, you can rewrite the first equation, equation 2 here, okay, as En equals to LAI dot A plus RAIA, and I think it was, yes, plus KB. Instead of theta dot, I'm going to just use omega. Okay, so with this, I have reduced the order of the system to to 2. Okay, I have one first order differential equation here and another first order differential equation here. Okay, and just like the previous examples that we solved, guys, note that if you solve equation 3, you will get theta. If you solve equation, let's say 4 and 5, okay, or equation 4 here, you'll get omega. Okay, so you will lose a little bit of information, okay, and it really depends on what you need in this problem to solve. Okay, so let's summarize. For modeling a DC motor, what we did was we somehow considered two domains of energy, electrical and the mechanical. Electrical one was dealing with the wirings and windings. And we did the lumped step approach, okay, or lumped mentality. We lumped all the resistance in RA, lumped all the inductance in LA, okay, and include the back electromotive voltage. For mechanical side, we lumped the inertia of the rotor in one inertia element, all the bearings, we lumped them in one viscous friction, okay, and we considered the torque from the DC motor as an external torque. And also we considered a little bit of a load torque. For each energy domain, basically we separated or divided our page into two sections. For each energy domain, we followed our four-step approach specific to that energy domain. And at the very end, when we were actually about to box the equations, okay, we used the equations for the gyrator to somehow link one energy domain to another energy domain. What was that equation for the gyrator? That was the two equations that we have here. Yes, that the torque of the DC motor was connected to the current and the back electromotive voltage was connected to the angular velocity. And at the very end, we mentioned that, okay, equation 2 and 3 are the ones that somehow describes the dynamics of the system. However, we can somehow work with these ones, okay, and reduce the order of the system by 1 by just simply substituting theta dot with omega and theta double dot with omega dot. I hope you guys find this helpful. I would assign a small homework for you guys to look into, okay, and work on this one. In this example, you see that I have the same DC motor, but this DC motor is connected to a gearbox, okay? And the gear ratio of the gear 1 and gear 2 are given to you as N1 equal to 10 and N2 equals to 100, okay? And I want you guys to work on this problem by your own, okay? Again, you can consider two domains of energy as mechanical on the right-hand side and the electrical on the left-hand side, okay? And you need to figure out what you want to do with the gearbox. Note that the gearbox is a transformer. It's not a gyrator. So in this problem, you have a gyrator and a transformer. Good luck and have fun.